Right. Hello, I'm David. I'm the coordinator of the Maths Learning Centre at Semester 1 2017, and I'm talking to the Maths 1M students. Hello from the past, those who are listening, and hello from the present, those who are here. I'm going to talk about complex numbers. So complex numbers fit in the story of the families of number right at the end. So at the beginning, in the beginning, for human beings, there were the natural numbers, which had a symbol n and started at 1, and allowed us to count stuff. Theory goes that actually the very first use of numbers ever currently on record is probably a woman counting her period. So women invented numbers, which I think is kind of cool. Okay, so there was natural numbers, and then there was 0, because the natural numbers count how many of something there is, or they count where something is in order in a list. And the answer to how many of something there is could be none. And so we have 0 as well, which was created in various different cultures at various different times, and they may or may not have had a symbol for it. And then there was the creation of the fractions, and at some point in the future there was the creation of the negative numbers, which were designed to calculate, to record distances in 2 directions simultaneously. So I'm going to leave off from history now and just talk maths. There's the integers, which have 0 in the middle, and they go the natural numbers up and the negative of the natural numbers down. These are nice, you can put them in order. And then in the next family of numbers is the rational numbers, called Q because it stands for quotient, and this is all of the things that can be written as fractions of integers. And so we have to leave off the way that we normally write about. We can't write them in a list. We can actually, but I'm not going to write them in a list. Between all of these integers and natural numbers, there are rational numbers which can be written as fractions. And the integers themselves can be written as fractions, so they count as rational numbers as well. And so we've got anything that can be written like this for m and n in the integers. Except the bottom's not allowed to be 0, because that's not a thing. And the rational numbers are useful for comparing the sizes of things and talking about how things change from one size to another, and describing lengths that are between the integers, and all very useful things. And back in the distant past, the Pythagoreans believed that the rational numbers were the only kind of numbers. But it turned out that there were other numbers called irrational, because they're not rational, and they are the real numbers. And they're really hard to talk about in terms of defining them, but a real number is any number that could describe a location on a line relative to 0. And the real numbers were awesome. The concept of the real numbers allowed us to talk about every point on a line, and fill out all possible distances and measurements of any kind that we could possibly think of, and they were awesome. And then later, people discovered that when they were attempting to factorise cubics, there were some neat little tricks they could do by pretending there was such a thing as the square root of -1. And much later, they discovered that they were able to represent a number plane. And they became the complex numbers, which are called C. there you go, there's a bit of some of its history. It's not quite in the same order it was invented. The positive rational numbers were invented before the negative integers, but this is how the mathematicians organise them, because everything's nice and self-contained. If you add two integers together, you've still got an integer, and subtract them, you've still got an integer. When you divide them, you don't get an integer anymore, you get rational numbers, but the rational numbers are nice and self-contained. If you divide two of them, you get a new one. Add them, subtract them, multiply them, there'll be a new rational number. You can't get out of the rational numbers if that's all you're going to use. You're going to have to use things like square roots to move yourself into the real numbers. And the only way to get from out of the real numbers is to do square roots of things that don't have square roots. And so the complex numbers were created, and after a couple of hundred years of research have gotten to the point where people understood them pretty well. And so, there you go. And so your complex numbers can be made out of your real numbers like this. So what we do is that we attach a new number called I, such that I squared is equal to minus 1. And then the complex numbers is all of the things that can be made like this. So this is, to read this notation, the complex numbers are the set of all things which are a plus b times I, such that a and b are in the real numbers. There is no... there you go. So what we discovered is that you could, if you wanted to create all these other numbers, like the square root of minus 5 or the square root of minus 17, things that square to give negative numbers, but it turns out we don't need to do any of that. I allows us to solve all possible quadratic equations that we couldn't solve before, which is kind of cool. In fact, it allows us to solve any polynomial that we couldn't solve before. And that's kind of a nice thing about the complex numbers. So, there they are. And that's pretty much all they do. You know, if you just assume that all of the normal rules of numbers work, you're allowed to multiply in any order you like and get the same answer. You can expand out multiplication over addition. All of those laws you assume work. And so you, that's not what I want. All of those laws for numbers work. And you can construct all of these things, and it turns out that a plus bi is enough to get all the extra things you need. So, just a second. I'm just going to look something up. Okay. Here's a problem for you to try. It's called the ice habit. Using any of the operations plus, minus, times, divide, and as many brackets as you want, and as many of the number I as you need, make each of the numbers on that picture. So minus 2, you could make, for example, minus 2 plus I, or 0 minus 2i, all of those things. So I want you to think about that for about 2 minutes and see which of those numbers you can make. Really, I'm serious. I want you to give it a go. Feel free to write, because, you know, that's what paper is for. If you want some focus, I want to ask you how to make the number 2 out of only I. Feel free to talk to people around you. Don't have to be quiet in line. There's all sorts of thinking going on. Well, it sounds like we've got something going on there. What was that?
You can use brackets, right?
Yep.
Use a bracket, negative I, take I, close the bracket, times I.
So you're saying that negative I, take I, times I, you say?
Yes.
Okay. So I could do, that'd be in the brackets minus 2i. And then minus 2 times I again, which is I squared. And minus 2 times, and I squared is minus 1. And so we get 2. Nice. Does anyone have another way of making 2 out of just I?
I to the power of 4 plus I to the power of 4.
How are you going to make your 4s? But I to the power of 4 would totally make, just bending the rules a little bit of the game, but I to the power of 4 would be I squared squared, and I squared is minus 1, and minus 1 squared is 1, and so that's a way of making 2. Doesn't follow the rules of the game because I'd have to make the 4 as well, but it's a very clever idea. I've got one as well that I've seen before. I plus I divided by I. Because I plus I is 2i, and I divided by I is 1. One of the messages of this problem is that A, it gives you practice at doing complex number arithmetic, which is a good thing to have practice at doing. And secondly, once you've seen a couple of the solutions, you can come to realise that you can actually do the same things that you can do to other numbers. I plus I divided by I, we forget that you can actually divide by complex numbers. And you can. I divided by I is totally 1. So it's okay to divide by them. It does cause some problems sometimes, and I'm going to get to that in a second. It's a really interesting thing to do, to instead of looking at an exam problem, to give yourself some other problem and say, well, what numbers can I make out of these? And give yourself some practice without having to have any particular goal in mind. There you go. That was fun. Okay. So, the thing about these complex numbers is they have multiple representations. And I'm going to start now talking about those multiple representations of complex numbers, because each representation is useful for different things. And the specific question that I was asked via email was, how do you decide which representation to use at any moment? And it goes with what they're good for and what they're not good for. So there are 3 representations of complex numbers, 3 main ones, and they go like this. There is this representation, like that, and you can see plenty of those. And there is this representation, which is a dot on a plane. And there is this representation, like that. So there are 3 different ways, fundamentally, to represent complex numbers. And just the same way as with a fraction, you could represent it as a fraction or as a decimal. And those 2 different versions of the way you write fractions or even as a percentage, those 3 versions of writing fractions are useful in different contexts. Same deal here. Now your lecturer has in the pictures in the lecture Though for those of you watching from the future, your lecturer may not do this because you may have a different lecturer, but this year's lecturer has traditionally drawn them as an arrow from the centre. That was just so that you could see where they were. But essentially it's really a dot. We're just locating things. In the same way that a real number can locate a point on a line, a complex number can locate a point on a plane. So the first thing when you have multiple representations is to know how to convert between them. So to convert between them, you can go, it's going to be easier with an example. 2 minus 3i. You can interpret the 2 as an x-coordinate and the minus 3 as a y-coordinate, and you can draw this point. So when we imagine complex numbers, that dot itself is the number 2 minus 3i. And if you see any dot you like, you can convert it to a complex number. This is the number 1 plus 4i. Even the dots on the x-axis. So this dot here is the number 3. And this dot here is the number I. And every dot on that plane has a complex number representation, and vice versa. Every complex number representation as an a plus or minus bi has a dot on the plane. And you can make the negative ones too. This would be minus 1 minus, looks like 4, it looks like 3i. Okay, there you go. For the what they call the polar form, something like that, that has a representation on the picture as well. And each piece of this is represented on the picture. So essentially this thing exists in its own right. The cis pi on 3 is a number all by itself. And that cis pi on 3 is a number that is on the unit circle. And it's an angle of pi on 3 from the number 1 on the x-axis. So we'll go pi on 3. Now what's pi? Pi is 180 degrees as an angle, as an angle in degrees. So that would be about there, a third of the way, and pi is that distance. So we're a third of the way around. That's a bit high for 60 degrees, I'm sorry. So that number just there, that black dot, that is cis of pi on 3. And if I multiply that by 3, it'll be out here instead. So this dot just here, that's 3 cis pi on 3. Okay, that's the locating. So I can turn both this rectangular form, I think it's traditionally called Cartesian form or standard form, and this form here, I can convert them both into dots on the plane. And given a particular dot, I need to figure out how far from the centre it is. And actually that's a worthy point to make out. This distance here is 3. Okay, so if I had something like, so to locate 3 cis pi on 3, I could find the distance 3 and then go around the angle, or I could go around the angle and then scale it out times 3. And if I just had a random dot in the middle of nowhere, maybe there, I need to figure out which circle it's on, how far from the centre it is, and figure out what the angle is. And that looks like 45 degrees, which is pi on 4. So this would be 2 cis of minus pi on 4 because my angle is being measured clockwise. Okay, interesting. One of the interesting things about this representation here is that every complex number has more than one way of writing it. Back in this representation up here, every complex number has essentially one way to write it. If you've got whatever this number is and whatever that number is are the x and y coordinates. Whereas with this, I can choose lots of different angles and they would all produce the same complex number. So I could go this angle and it would produce that complex number, but this angle too would produce the same complex number, and this angle here would produce the same complex number. And so I have multiple representations of every complex number using this version of representing them. So I'm going to leave off the 3, I'm just going to do it with the cis. Cis pi on 3 could just as easily be, let's see, 1, 2, 3, 4, 5, 6, 7 pi on 3. And it could just as easily have been minus 1, minus 2, minus 3, minus 4, minus 5 pi on 3. And they're all the same number. Not to say that the angle pi on 3 and the angle 7 pi on 3 and the angle minus 5 pi on 3 are the same angle. They are not. They are different lengths. They go around in different directions and at different amounts of distance. But when I do a cis on it, it produces the same complex number. So these are the same number. All right. So what we need to do is finally is to be able to convert something like this into something like this and vice versa. And the way that we do that is via the picture. You don't have to do it via the picture, but that's how we understand how to convert between them. So to convert between them, we need to figure out what corresponds on the picture. And so this is how the picture goes when they're both in there at once. The x-coordinate could be measured along here. The y-coordinate could be measured along here, and that would be the point A plus BI. And you could measure the distance from the centre, and you could measure the angle, and that would be r cis theta. Now, it's not always true that A plus BI is r cis theta if your A's and B's are different. Like, the idea is that those are just placeholders for what numbers go in this picture. Yeah. But this is how it tells us to figure these things out. I can use this little right-angled triangle here to tell us how to figure out what this r is, because r squared should be equal to a squared plus b squared. And this theta, well, tan of this angle should be b divided by a. Based on some right-angled triangle trigonometry. Okay, so actually, this is the harder one to do. Interesting that I'm choosing to do it first. So it's easier to see as an example. Ooh, is that going to work? Sorry, it's always hard to think about the ones that will come out to exact answers. Okay, so this number here, I need to try and figure out what that is as a polar form. So, easiest to draw it. It's 2 and 2 root 3, which is sort of a bit longer than 2. So there it is there. Like that. And I need to figure out how long it is and what angle produces it. Okay, so let's see. I'm going to draw on my diagram. Like that. So let's see. I know that r squared is going to be this real bit squared and this bit attached to I squared. I'm not going to include the I because that's just holding where my y coordinate is at the moment in this representation. Okay, it's a literal distance here, and that distance is a real number. So 2 squared is 4. When I square, I can do them separately. 2 squared is 4, and root 3 squared is 3. And so I get 4 plus 12 is 16, and so r is 4. Now I don't have to do a plus or minus when I do this square root, because r is a literal distance from the centre, so it can't be negative. It's just measured from 0 outwards. Okay? And I also know that according to this triangle, that tan theta is 2 root 3 on 2. Which is root 3. And normally, if I saw a triangle with tan theta as root 3, I'd be expecting it to look more like this. And so if tan is root 3, it will be opposite over hypotenuse, so that should be 60 degrees, which is pi on 3. Lovely. And I'll just check to see if that makes sense. An angle of pi on 3 would totally, if I start in this corner, still be in this quadrant here. So I'm in the correct quadrant, so it really is the correct angle. And so therefore 2 plus 2 root 3i is the same as 4 cis pi on 3. There you go. That's one way of doing it. There are others. What you could shoot, well, I'll do another example just to show you something really important that you're not supposed to do. Minus 5 plus 5i, let's convert that over to the other format. Well, first I'll figure out the length. Well, first I'll draw it. It's over here. Okay. So I'll label my diagram. Just put the r in. R squared is minus 5 squared plus 5 squared. Plus 25, which is root 50. Okay, that's 50, so r is going to be the square root of 50. Really should have left it as 2 times 25, shouldn't I? No, that's not a 5. Root 2. Because I can square root the 2 and get the root 2 and square root the 25 and get the 5. So like that's the nicest version of that number. Okay? Sweet. And now I will figure out the angle. So this angle just here is the one that fits inside my right angled triangle. It's 5 high and 5 wide in this direction. And this angle here, which I'm not going to call theta for important reasons that will become clear shortly. Okay, according to this picture, which is 1, which means that this has to be pi on 4. Because I know that tan alpha is 1 when alpha is pi on 4. But the thing is that the theta that I'm looking for isn't inside this triangle. It's over here. And so my theta is really, well, let's see, if that's a full pi there and that's pi on 4 there, I'd have to have, so that's a quarter of pi, 3/4 of pi. So the theta that I need to do my polar form isn't inside that triangle. And so therefore we've discovered that minus 5 plus 5i is in fact the same as 5 root 2 cis 3 pi on 4. What it's wrong to do is this. It's wrong to say that theta is tan inverse of the imaginary part divided by the real part. This is wrong. It's not true. Because when I calculate this, I get tan to the minus 1 of minus 1, which is minus pi on 4. And this angle here is not minus pi on 4. Minus pi on 4 is here. So you cannot say, if you write down that the theta is the theta in the r cis theta, then you can't say that it's equal to tan inverse of the b on a, because it's not always true. You have to say that tan theta is equal to the b on a, that's always true, but it's not true that theta is equal to tan inverse, because tan inverse only comes out to angles between plus pi on 2 and minus pi on 2. And so you can't produce the angle you want. You need some other way of writing it so that the angle you want is tan inverse, and then you construct you need some way of constructing it so that you have some other angle that's tan inverse, and then you make your angle out of that. I find the easiest way to do it is this way, and to find an angle that's inside a right angle triangle and then make the angle I want. I don't use tan inverse at all usually. If I had to, this is where I'd use it, because this angle is totally inside a triangle and tan inverse will work for an angle that fits inside a triangle. Yeah. So, yeah, don't get me started on tan inverses B on A.
So is it fair to say that you always measure the angle in cis from 0?
Yes, the angle in cis is always measured from the number 1 on the x-axis.
Okay, but you can go clockwise as well.
You can go clockwise, but then it's a minus angle. So yeah, you'll always go anti-clockwise from here, but if you want to go clockwise, it'll be a negative angle. All right, so that's the hardest conversion. The easier conversion is going the other way. Just as an example, if I had 3 cis, I don't know, pi on 6, then the important thing in my head is I don't really care about that 3, it's what cis means. The letters cis are an acronym, they stand for cos, I, sine. And so I can use that to remember what to do. But I can also do it straight from the triangle here. Using trigonometry, cos of theta will be A on R, and sine of theta will be B on R. And so I can figure out what the A and the B are in terms of R and theta. So as it turns out, cis by itself is cos of the angle plus I times sine of the angle. And then this 3 is literally multiplying that number by 3. It's not just a notation that we write it next to it. It really is 3 times the number cis pi on 6. So what is cos pi on 6? There. So cos pi on 6 is root 3 on 2. And sine pi on 6 is 1 on 2. And so it's not particularly edifying. But I can now multiply out the 3. Some people like to do that multiplying out right at the beginning, before they've even calculated what the cos and the sine are. I don't think about it that way. Okay, so this direction of converting is easier. Okay. Well, some practice, eh? Or is it here? Yeah, it's gone. Here it is. Okay. Maybe not yet. All right. So that's converting between the different representations. It's not necessarily, particularly edifying, but it's useful to know that each representation in written maths corresponds to something in the picture as well. And that relationship between complex numbers and geometry was not realised very early on, and that was the thing that really made complex numbers useful later on, is that they could represent points on a plane. Okay, so what have we done now? We've converted between the representations. If these really are numbers, then we should be able to do all the operations that we normally do on numbers. All right. So we should be able to add them. We should be able to add and subtract them. So let's see what that looks like in each of the representations. Wow, all right, add and subtract them. Here is the number 3 plus 2i and the number I, and if I want to subtract them, that's all right, I'll just do algebra. So 3 doesn't have any i's in it, so it will stay as it is, and the 2i minus I will come out to 1i. Ta-da! That's pretty much all there is to it. Yay! Just be careful when you're expanding brackets that you don't lose your minus signs, that's a classic problem. This isn't going to be nice, but let's see. So the minus does what minus always does. I can expand the brackets with the minus and expand it over plus. And so I've got minus minus 2, which is plus 2, and minus I, which is that. And unfortunately, root 3 and plus 2 aren't going to add nicely unless I use decimals, and so I'm just going to leave them as they are. But I can combine my i's. Beautiful. I mean, that's lovely. It would be nice to know what addition and subtraction did to the numbers when they were drawn as points on the complex plane. So let's do... Maybe not that one. Well, maybe. Well, okay, just a second. There's two things happening here. In algebra, subtraction doesn't really exist. It's just adding the minus version of something. And so what we really need to know is what does minus do to something, and what does adding do, what does negation do to something, and what does adding do. So if I had a random number like, 2 minus, 5's too long. 2 minus 3i, there. And then I minused it. Minus of 2 minus 3i would be minus 2 plus 3i, which is over here. Which is exactly in the opposite direction. So when you do a minus of a complex number, it ends up pointing in the opposite direction, which is exactly what minus did to real numbers as well. Plus 2, plus 5, and minus 5 were pointing in opposite directions. It's just that we have more space to do that. And that's why the arrows are kind of useful, because the things that we do to them are the same as the things that we do to vectors. Okay, so let's see. Minus of a complex number, it's traditional to call them z, is same as z, but in the opposite direction. That's kind of cool. And when you add complex numbers, the easiest way is to treat them as vectors and stick them head to tail if you're going to do it in pictorial form. I mean, the easiest way to add complex numbers is to use algebra. But slightly less easy, but also something that you could do is if you wanted to do it with pictures, you could do three plus 2i plus minus 2 plus I. Well, 3 plus 2i is here, and minus 2 plus I is here. And what we can do is we can treat them as vectors. 3 plus 2i looks like that. Minus 2 plus I looks like that. And what we can do is we can actually stick them head to tail. 3 plus 2i and minus 2 plus I is like that. And this is my new answer just here, which looks like it's 1 plus 3i. And my algebra checks out. Beautiful. Okay? I can stick my arrows head to tail just like you do with vectors and produce a new number. Alternatively, you can't see that, can you? Alternatively, I can think of the first one as a location and the second one as a journey. I started at the point 3 plus 2i, and I went from there, the journey minus 2 plus I, and I ended up at this new point here. Okay, so that's how it works. That's how the addition works for the pictures. How does addition and negation work for polar form? Well, it doesn't. Polar form is no good for addition. It's not useful for addition. If you have things in polar form and you want to add them, the quickest way is to turn them into Cartesian form and then add them then. It just isn't a thing that works. For negation, this is kind of interesting actually. What about negation? Now, this is a perfectly reasonable thing to write. There is a number which is minus cis of pi on 3. But traditionally in polar form, you don't write it with a minus out the front. You always write it as a plus cis something. So somehow I have to convert this into some other... If I want this in polar form, I'm going to have to make that not a minus out the front. Well, I can do that by thinking about where it is. So cis pi on 3 is Starting at 1, we go pi on 3, which is about there. Cis pi on 3 is there. That's a bit high, I'm sorry, but it's about there. And I know what minus does to the picture. It reverses it through the origin. So this arrow, when I do minus, is this arrow. Gorgeous. And if I want to write that in polar form, I just need to figure out the angle that gets here, which is this angle here. So let's see. Well, I guess if this is pi on 3, because it's a reflection, that would be pi on 3 as well. And so that would be a full pi, minus pi on 3 would be 2 pi on 3, but it's backwards, so it's minus 2 pi on 3. Whew, okay. If this is 60 degrees, then this has to be 120, but it's backwards, so it's negative. So that was kind of interesting. So it looks like minus cis of pi on 3 is the same as cis of minus 2 pi on 3. And the difference between these two is pi. So putting a minus on the outside of the cis is the same as subtracting pi from the angle on the inside. Okay, that's kind of interesting. Something interesting is going to happen in a minute, and we'll deal with that in a second. I could also have added pi, and it would also work. Okay, so what have we done? We've done plus and minus. Good, let's do times. Okay, so let's see. We're going to multiply now. So when we multiply complex numbers, well, let's do it in all three formats and see what we get. We're just going to expand. We're just going to expand the way we do with all ordinary algebra. 2 times 5 is 10. 2 times minus 2i would be minus 4i. I times 5 would be 5i. And I times minus 2i would be minus 2i squared. And 10, so minus 4i plus 5i is just I, and I squared is minus 1. So 10 plus I plus 2, it looks like it comes out to 12 plus I. Sweet. That's multiplication. Yeah, not particularly nice, but thing I could do. Really interesting thing actually about the way multiplication works is that it's similar to doing polynomials in modular arithmetic, which is just awesome. But not going to get into that today. What about in polar form? Now, the thing in polar form is that the polar form is made of two pieces. It's got a real number and a part with a cis. And we know how real numbers multiply, so we don't have to worry about that part. The key is to know what happens with the cis. It's not going to be easy to figure out what the answer is in rectangular form, but I'm not going to worry about that. So when you multiply two cis's, you'll just add the angles. Which is why cis is so awesome for multiplication. It's crap for addition, but it's nice for multiplication. So I can just add the angles. Now they're fractions. I suppose I could put them over a common denominator if I really felt like it. 4 pi on 12 and All right, there you go. It's not particularly edifying, but there it is. When you multiply sis's, you just multiply the angles. And I did say something about it. You know, if I had 5 cis pi on 3 multiplied by, 8 cis pi on 4. The thing is, these are just numbers. There's 4 numbers here. There's 5 and cis pi on 3 and 8 and cis pi on 4. And multiplication with any numbers, including complex numbers, you can do in whatever order you like. And so there's nothing stopping me doing the 5 times the 8, which is 40, and the cis pi on 3 and the cis pi on 4, which is cis 7 pi on 12, which I already did earlier. So there's nothing stopping me multiplying things in whatever order I want, because multiplication I can do whenever I want. So it's not really that there's a rule for multiplying complex numbers in polar form, there's a rule for multiplying cis. Sweet. Beautiful. Okay, nice. So I just want to show you something, and I think it's kind of cool. You know how we did minus cis of pi on 3 before? We can figure out what that is using the properties of multiplication of cis. Because minus is the same as minus 1, right? And minus 1, let's see, minus 1 is there, and it's 1 long, and it has an angle of pi, or even an angle of minus pi if I liked. So this would be the same as cis of pi. And when you multiply cis's, you add the angles. Yay! Isn't that nice? I could just as easily have used minus pi if I wanted. So that's an alternative way to get the same answer. I could have thought of it as putting the cis pi on 3 on the opposite side and figuring out the angle that gets there. Or I can think of the minus 1 as a cis of its own and just use the multiplication rule for cis, which I think is kind of cool. I like having multiple ways of doing things. Okay. It's really good to know how multiplication works on the diagram of the complex plane as well. And as I said, this doesn't make all that much sense on the diagram. It's not particularly easy to follow. But there are 2 things that you can figure out about the way multiplication works on the diagram, and it's multiplication by a real number and multiplication by a cis. So on the diagram, multiplying by a real number corresponds to a stretch outwards. So if I had this as my z, or maybe this as my z, then 3z would be here. 3 times further away from the centre than z is. Okay, so multiplying by a real number is a stretch outwards. And multiplying by a cis of an angle is rotation by that angle. So if I had my z, say here, then if I rotated it by maybe, I don't know, pi on whatever, if I ended up over here, and that angle was, I don't know, it looks like about nearly pi on 2, then this would be z times cis pi on 2. That's a really useful thing to know about the way these things work. Multiplying by a real number stretches it out, multiplying by an angle rotates it. If that angle is negative, you'll be rotating clockwise. If the angle is positive, you'll be rotating anti-clockwise. And that's a really useful thing to know about it. And it does make sense of your addition thing when you multiply. If multiplying by an angle by a cis rotates it, well, we'll start with 1 and we'll multiply by cis pi and 3, which will rotate it around pi and 3, and then multiply it by cis pi and 4, which will rotate it a bit further, and that's why you add the angles together, because you just keep rotating further than you're already up to. That realization that cis multiplying by cis rotates things was a huge realization when they did their geometrical version of complex numbers. It was a big thing. And ultimately, it resulted eventually, after about a couple of hundred years of research, ultimately resulted in the cross product in 3D, which is kind of cool too. Okay, so what have we got? We've got addition, which we can do by just adding the like terms if it's in Cartesian form, and we can't do if it's in polar form. And if it's a drawing, we can do it as vector addition by putting arrows head to tail. We've got multiplication, which is expanding brackets if we're in Cartesian form, and is multiplying cis's is adding angles in polar form, and is rotating and stretching if you're in the picture. So the last operation that we might want to do right now is, we're going to have to do powers as well, is division before we do powers. So division is really nice in polar form. When you divide cis's, you subtract the angles. Yay! And I happen to know that a half minus a third is a sixth because it's my favourite fraction fact. But actually, if you subtract two fractions, like 1 over something, where the something is 1 apart, it'll always be 1 over the multiplication of them. So a third minus a quarter is a 12th, for example. But this is my favourite one. So there you go. That's fabulous. So just, yay. And since the other numbers that are involved in polar form are just plain numbers, we can just treat it the way we would normally treat it. If I had like... division and multiplication can be done in any order you like, as long as the things that are divided when you want. And also, like with fractions, we can just cancel things out if we need to. So 15 divided by 5 is 3, and cis pi on 2 divided by cis pi on 3 is cis pi on 6. Okay? The real number parts can be treated exactly the way you treat all real numbers in fractions, because they are real numbers, and fractions behave the same in complex numbers as they do in real numbers. So there's nothing stopping you just dividing things that can be divided. And if that wasn't a 5, it didn't go into the 15, if it was 15 on 2, you would just write 15 on 2. Complex numbers. The real numbers are part of the complex numbers, so they have to behave nicely. Okay, that's great. Division is awesome. It makes complex, polar form makes division really nice. Division in Cartesian form is really hard compared to all the other things. Actually, before I get to that, if I just had this is not hard. Okay? Because I know how division expands out under addition, because I know how algebra works with real numbers, and the algebra works with complex numbers exactly the same way, and so there's nothing stopping me just dividing them separately by the 6. Okay, so I know how to divide by real numbers. It's beautiful. And that is the key to doing division in Cartesian form. What we're going to do is rewrite it so that it's division by real numbers, and I know how to do division by real numbers. Now, it would be very nice if I could just divide everything separately, you know, divide them both by 6 and divide them both by minus I, but that's just not how division works. I could, if I really wanted to, go, you know, I'm just going to write this and then I'm going to rub it out. This is totally a thing I could do if I wanted. Algebra works the same, I can do the denominator on both of them. It just doesn't help, okay, because I still don't know how to divide by 6 minus I. It's nothing, you know, it's the same answer, I just don't know what it is. So that's not going to help, even though it's something that I could do. What I'm going to need to do is somehow convert this fraction into something that has a real number on the bottom. Ah, interesting. So I need a way of turning this into a real number. And I'm sort of getting ahead of myself because there's an operation I can do on complex numbers which will allow me to figure out a number that will turn that into a real number. But really what I want to do is this. I want to go 5 plus 2i. It's really bad, I'm sorry. Okay, and I want to multiply, because it's a fraction, I'm allowed to multiply the top and bottom by something, by anything I want really. I mean, I could multiply it by 15 or 17 or minus I if I really wanted, and somehow turn that into a fraction that has a real number on the bottom. And the nice thing is that if I do this, if I just switch the plus or minus on the I part, actually I could switch the plus or minus on the real part too, just one or the other, but not both. It will happily turn this into something that has a real number on the bottom. So if I expand out the top, I'm going to get 5 times 6, which is 30, 5 times I, which is 5i, 2i times 6, which is 12i, 2i times I, which is 2i squared. And on the bottom I'll get 6 times 6, which is 36, 6 times I, minus 6 times I, nice, they cancel each other out, and minus I squared. So let's see, 30 plus 17i, now I squared is minus 1. So I get 28 plus 17i over 37. And that I can do because now I have a real number on the bottom. Yay! Yay. So this is really interesting here, this trick here, in essence it is a trick, to figure out a number I could multiply the bottom by so that it turns out to be real after all. That's interesting. I'm not going to draw what division looks like on the picture, because it's not at all easy, but dividing by a real number usually means shortening something, if it's a big real number. If dividing by a half would be doubling the length. But division isn't a real thing, right? Division is just multiplying by something. So dividing by 2 is really just multiplying by a half. So, and then that's essentially what we did here. We said dividing by 6 minus I is the same as multiplying by 6 plus I on 37. So there you go. Okay. So we've got addition, subtraction, multiplication, division. Powers would be the next one. I'm not going to actually calculate this, but totally a thing you could do, right? 5 plus 2i, if you wanted to do it to the power of 7. 2i, 5 plus 2i, 5 plus 2i, times 5 plus 2i, 5 plus 2i, 5 plus 2i, 5 plus 2i, and expand it all out, and you'll get an answer. You could, if you knew the binomial theorem, do that slightly quicker if you wanted. So you could go 5 to the 7, and then 7 choose 1 times 5 to the 6 times 2i, plus 7 choose 2 times 5 to the 5 times 2i squared, and just do that if you wanted, but that's a thing that you could do. It's just expanding brackets, except that at the end, when you get all your I whatevers, your I squared becomes minus 1 and your I cubed becomes... Actually, that's a useful thing to do before we move on. Let's do powers of I. Powers of I are nice. I like the powers of I. I to the 1 is I, and I squared is minus 1, because we knew that, that's definition. And I cubed would be multiplying this by I, because I squared times I is I cubed, so that would be minus I. And I to the 4 would be minus I times I, which would be minus I times I, which would be minus I squared. And I squared is minus 1, which is 1. Okay, beautiful. And then I to the 5 would be multiplying that by I, which is I. And I to the 6 would be multiplying that by I, which would be minus 1 again. And I to the 7 would be minus I. And I to the 8 would be 1, and so on. The powers of I go round in circles, which I kind of should have expected, because I know that multiplying by I, because I is cis pi on 2, is rotating by pi on 2. So essentially the picture is this, right? There's I, which is rotating by pi on 2. There's I squared, because that's doing that twice. And there's I cubed, and that's doing that 3 times. And there's I to the 4, and there's I to the 5, and there's I to the 6, and so on. It just goes round and round and round. The really nice thing about this is the powers work in the opposite direction as well. Here's I. Well, I to the 0 is 1, and let me go the other way. All right, so I to the 1 is I to the 0 is 1, I to the minus 1 is minus I to the minus 2 is minus 1, I to the minus 3 is I, and you can go backwards around the circle if you want with the negative powers. It's kind of cool. So look at this. I to the minus 1, which means 1 over I. 1 over I is minus I. It's a little bit freaky, but there you go. So that happened right at the beginning, which I was very happy that you presented that answer to the right at the beginning. Look at this. Multiplying by I. Well, technically we had I plus I times minus I, which is the same as I plus I divided by I, because dividing by I is the same as multiplying by minus I. Isn't that cool? Gotta love complex numbers. Okay, so the powers of I are really nice. In fact, the powers of anything that you could write in polar form are always really nice, because, and this is de Moivre's theorem, I know de Moivre's theorem doesn't normally look like this, but I don't really care what the powers of the real numbers do, because I know how powers of real numbers work. All I need to know is how powers of cis works. That's de Moivre's theorem, essentially. Technically, it only works when n is an integer. The reason it doesn't work when n is, say, a half is because when you do the square root of something, there ought to be 2 answers, and so it's a bit ambiguous to say that it's cis of half of theta. When it's not just that, it could be something else as well. So it only works for whole numbers, but it does work for the negative powers as well. And this makes sense, because multiplying by cis theta would be rotating by theta, and doing that, multiplying it by n times would be rotating by theta n times, which is exactly what this means. So just as an example, if I did 3 cis pi on 4 to the 3, then the rules of powers and multiplication for real numbers say that I can do the 3 things. I can do both of those powers separately. And 3 to the 3 is 27, and cis pi on 4, well, when you do cis to a power, you just multiply by the thing. Yay! Now, it is traditional, since there are multiple options for how you write a complex number with a cis, it's traditional to choose your angle to be the shortest possible angle that gives that number. So when they say the principal argument, they mean the shortest possible angle. And so I'm just going to... That should totally be 27, thank you. There were just too many 3s on the page and I just got into a groove. Thank you for telling me. You should always tell me if I do something wrong. I wish I had things to give you as a reward, but I don't. I've got Play-Doh, but it's not good for eating. It's a bit too salty. Okay, though it's not toxic, at least not this Play-Doh because it's homemade. 3 pi on 4, oh, that's a perfectly good angle. I don't have to worry about that. That's there. Okay, I don't have to convert that any other way. It's already the shortest angle that could possibly get there. If it had come out to be, if I had done to the power of 5 instead of 3, then I would have ended up at 5 pi on 4, which is down here. Let me just do it again. So that would have been 3 to the 5 and cis pi on 4 to the 5. It's not actually necessary to do this intermediate step of working if you don't want to. That's how it works in my head. And 3 to the power of 5 would be 243. Just because I happen to know the powers of 3 up to 3 to the 5. Don't know it after that. I think it's 243. Yeah. No. Yes, okay, cool. Because 8 times 4 is, times 3 is 24, yes. Okay. Okay, so 5 pi on 4 is here. 1, 2, 3, 4, there. And that is not the shortest angle that gets to this spot. This is the shortest angle that gets to that spot. And so that would be the same as 243 cis minus 3 pi on 4. Because it's 1, 2, 3 pi on 4s. I really should have mentioned that as a thing earlier, but whatever. Converting to principal argument. Okay, so that was powers. Powers are fine. I can do powers if they're in polar form. What else can I do to complex numbers? Well, one more thing about powers, which is worth mentioning, is not technically in your course, but you need to know. I can do imaginary powers of numbers as well. So I can do number to a complex number. Okay, we've only so far we've only done complex number to whole number power. Okay, doing it to a fractional power, whole different thing, and that roots is we'll deal with that shortly. I can do real numbers. I can also do imaginary numbers to imaginary powers, but that's getting really bizarre. Real numbers to imaginary powers I can do, and I just wanted to write this down at the moment. So yes, this is defined to be this. There you go. It's defined to be cis of theta. There you go. Yay. It's not particularly edifying, but that's okay. And if I wanted to do, suppose I wanted to do 2 to the pi I, for example, well, I would have to rewrite it as e to the pi of something. And so I would go, well, 2 is e to the ln 2 like that. And so that would be e to the ln 2 pi I, and that would be cis of ln 2 pi I, which would be about, now ln2 is a little bit less, it's about 70%, so 70% of pi, no I there, sorry, no I. 70, about there. Yay! Really weird. But there you go. So if you take a real number to a purely imaginary power, you always get a complex number on the unit circle. There you go. It's just odd. Not a thing you need to worry about at the moment, but it's worth noting that if you go online and look at complex numbers, many places in the world do not use the notation cis. They only use this notation. So it's something that's useful to know about when you go looking online for things about complex numbers. When they write something in polar form, they will write the cis theta as e to the I theta. Just so you know. All right, so where were we up to? Roots. This is taking a lot longer than I was hoping, but I might as well do it comprehensively. So, now, so with real numbers, I can do roots, you know? E.g., the square root of 7t, damn it, the square root of 49 is 7. Yay, I know how to do that. It is not plus or minus 7, it's just 7. Okay, when we defined the symbol, this symbol here, we define it to mean the positive square root. Okay, if we were solving equations, then we would say that x was equal to plus or minus 7. So the difference here is that this one I am attempting to solve an equation, and this one I'm figuring out a single number. Completely technically, look at this. Root 49 is a positive number, and that's why it makes sense to put a plus or minus out the front of it. If it could be negative, then plus or minus of plus or minus would be ambiguous, and what would it even mean? And so that's why you just be careful about the way you write about it. And this is the key thing here that makes us worried about complex numbers to half powers. I mean, essentially this is the same as 49 to the power of a half, right? It's going to be really hard to consistently define what square root means for complex numbers. Okay, because I know that there ought to be 2 square roots for every number. That's how complex numbers behave, and all numbers behave that way. There ought to be 2 square roots for every number. But how do I consistently decide which of them is the positive square root when they're imaginary? Because it's not like I is actually a positive number. It's an imaginary number. Minus I is not negative, it's just the opposite of I. And in fact, I could just as easily have, live in another land where instead of I as my square root of minus 1, I had chosen minus I and called that I instead, and then the original I would be minus I. And it would all still work. And so I can't decide. And so I need to be really careful, and that's why there is no such thing as the square root of an imaginary number. There is such a thing as solving things like this. And so that is what I'm going to talk about now. So we talk about the roots of unity, or the roots of a complex number. What that means is solving the equation x to the something or z to the something equals your complex number. The z really makes me uncomfortable. I prefer to call everything x, but it does get confusing if you've got an x plus I, x plus iy. So I'm just going to keep it as z. I did this one already. I did the polar form of that already, didn't I? Yes, I did. Good. Okay. So powers and division and multiplication are easier with polar form. Okay, I could imagine a number which would be, something plus something I to the power of 5 comes out to this result, and I could expand it all out and get that, and that would just be a waste of everybody's time because polar form works so much nicer. what was it, 4. Okay. Oh, can I do z to the 4 instead? That'd be more fun. I.e. easier. Okay. All right, so this 4 is a coincidence, just it is not, that's not, yeah. Okay, so that's 4 cis pi on 3. So what we're really solving be very careful. Some people who are new to this area, actually a lot of people who are new to this area, and they're trying to concentrate on a lot of things all at once, and so it's easy to get things in the wrong spot. What a lot of people will do when they first come to this area is they will put this in the position that z's in. And then they'll do this to the power of 4. And that's not what we're trying to do. We're trying to say that something to the power of 4 produced this result. So what we're going to do is we're going to say, well, what if... Let's write the z in polar form too. For some r and theta. And then nice. And so we're going to get this. That's good. That's good. Okay, so the lengths of complex numbers work perfectly well. Okay, the lengths of complex numbers, if two complex numbers are equal, then their lengths will have to match. And we know that the length of cis is always 1, and so we can do this. So we can say that r to the 4 is equal to 4, and therefore r is the 4th root of 4, which is the same as the square root of 2. Okay, so we can do that bit. And we know that 4 theta and the pi on 3 have to match. The two cis's need to match each other. But the problem is that complex numbers in cis have multiple representations. And so 4 theta could be pi on 3, but it could be any of the other angles that produces the same answer as cis of pi on 3. And so I'm actually going to have to go back and fix my working so that it covers all the other angles that could possibly produce this number just here. And I didn't leave room for that, sadly, so I'm just going to have to fix that while I'm at it now. So let's see. All right, so note that cis of pi on 3. All right, so I've got two choices for how I'm going to write this. I can either explicitly write down several different angles that produce the same complex number when I put them into cis, or I can be unexplicit about it and say, well, if I go around a full revolution from there, I can get the same number without the same angle and just do that in algebra. So choose whichever one you like. I'm going to do the algebra version right now. Okay, cis of pi on 3 is the same as cis of pi on 3 plus 2 pi k for any k in z, z being the integers. Okay, so the idea is that when k is 0, well, it's obviously the same. When k is 1, we've gone round to 2 pi, which is a different length angle, but it produces the same number when I do cis. I could have gone 4 pi or 6 pi or 8 pi, or I could have gone minus 2 pi or any of those things, and they would all produce the same answer. And so what I end up with is that 4 theta could be any of these angles. I'm just going to leave it with the k. They know what the k means when they read this now, because I've said it's any k in integer. And so my theta becomes this divided by 4. Okay, nice. So let's just have a look. So my z has a length and an angle. Let's have a look at where they are. All right, pi on 12, let's see. That's pi on 4. Pi on 12 would be there's cis of pi on 12 there. And if I make this root 2 wide, then that's my angle. So if that's root 2, then this will be root 2 cis of pi on 12. Now let's see what happens when I add pi on 2. I end up just here. And if I add pi on 2 again, I'll end up just here. And if I add pi on 2 again, I'll end up just here. And if I add pi on 2 again, I'll end up back where I started. And so adding enough, making my k big enough, will just repeat the same 4 answers that I've already got. And so there's only 4 answers after all. And what I want to do is, because we like principal arguments and we want the shortest angles that produce our 4 answers, I'm going to do these 2 this way and these 2 this way. So actually, z is root 2 cis of pi on 12, which is that one, and root 2 cis of 1, 2, 3, 4, 5, 6, 7 pi on 12. That's that one. And also this one down here, which would be root 2 cis of minus 5 pi on 12. And this one over here, which is almost a full pi, root 2 cis of minus 11 pi on 12. Right, they are all my solutions. If you really want to, you can pick your values of k and do your little algebra. I find it easier to just count by pi on 12s in my diagram. Now, knowing that this is going to happen, knowing that a z to the 4 equation is going to give you 4 solutions, means that you can, if you want, instead of doing this, you can just pick 4 different angles that produce your thing back here at this stage instead of using the k. So an alternative way of doing the working, an alternative way of doing the working is to go cis of pi on 3 is cis of pi on 3 and cis of add a 2 pi. Well, let's just see. What's 2 pi in pi on 3? That's 6 pi on 3, right? So 7 pi on 3, and it's also cis of minus 5 pi on 3, and it's also cis of minus 11 pi on 3. And you just sort of keep adding or subtracting pi on 2s to get the 4 shortest angles that produce this, and then when you do your 4 theta etc., then you can go that the theta must be all of these divided by 4, and you just get your 4 answers straight up. If you want to do it that way. On different days I feel differently, and so I choose different answers. But almost always, to be fair, I actually find counting around the circle in lots of pi on 12 the quickest way of me figuring out what to do here. But you get to choose. And so on until you get your final answer. So one of the things that are many people are interested in is the roots of unity, they call them, which is the roots of 1. And so just be aware that when you do solve an equation like this, I'm not going to do the whole thing, z to the, I don't know, 16 is 1, which will have 16 different answers. What you're going to do is first you're going to turn 1 into polar form. And 1 is just there on the x-axis, and it has one of its angles is 0. But it's also 0 plus 2 pi and plus 4 pi and plus 8 pi, no, 6 pi and 8 pi and 10 pi and 12 pi and minus pi, no, it's minus 2 pi and minus 4 pi and minus 6 pi. And so you can say it's and then you continue from there and you divide those angles by the 16. And so I'm going to get that Z is eventually, if I do it all properly. Here you go. And there will be 16 of them. There'll be pi on 8 and pi on 4 and 3 pi on 8 and pi on 2, and there'll be 4 of them in each corner, and you'll have several of them going this way and several of them going this way. One of them will be minus 1. Yeah. But when they ask with a 1, just be careful. It's so easy to look at the number 1 and think it's a real number and therefore not convert it into all of its possible sisses. So don't get distracted by the fact that it's real. Real numbers are complex numbers too. So what have we done now? We've done addition and subtraction, we've done multiplication and division, we've done powers, and we've done roots. I think that's pretty comprehensive of things that you can do to numbers. But complex numbers have one more thing to do with them that you can't do to real numbers, and that is conjugation. We can, conjugation. You can conjugate complex numbers, and this is one more thing that you can do to them that you can't do to real numbers, or at least doesn't do anything to real numbers. So you know how I said that when we did that I squared is minus 1 right at the beginning, well, minus I squared is also equal to minus 1. So when we first defined complex numbers, we had two choices for which number to use to be I, because every number has 2 square roots. So we could have chosen one, this I or that I. And it turns out that it doesn't matter which one we choose, it still looks the same. And that's the idea of conjugation. Okay, so the entire of the complex numbers in terms of the structure of them and the shape of them and the way they're arranged in the complex plane is exactly the same if you used I or minus I. So it shouldn't change any of your operations, it shouldn't change rotation or multiplication or powers or any of those things if you switch all your I's for minus I's. And it doesn't. It's very nice. And that's conjugation. Okay, so no operations by switching I with minus I. And it's true, okay? And that's the idea of conjugation. If I have a complex number, then the conjugate is what I get by switching my I for a minus I. Or my minus I for an I, doesn't really matter. So why do I care about making conjugates? I care about making conjugates because it is the one operation which will not be affected by addition or multiplication or division or powers. Okay, so the rules go like this. If I have two complex numbers, which I shall call Z and W just because, if I add them together and then do the conjugate, it will be exactly the same answer as if I did the conjugate and then added them together. If I multiplied them together and then did the conjugate, it would be exactly the same answer as if I did the conjugate first and then multiplied them. And if I divided them, it would be exactly the same. And if I did powers too. damn it. Z squared conjugate is the same as Z conjugate squared. It even works if the complex number is in the power. But I'm not going to go there. Okay? This is a really special thing. Okay, so with real numbers, no function expands out over both plus and times. Okay? So you're used to, sine and cos, for example, which don't expand out over plus and they don't expand out over times. You're used to maybe three times number can expand out over plus, but it can't expand out over times, because if you had 3 times xy, it's not 3 times x then times 3 times y. That doesn't work. Conjugation is pretty much the only function that expands out over both addition and multiplication. Really cool. Yep. No, you're not asking? No, you were just flicking your pen? Okay. The other thing that conjugation does, which is really nice, is that it does this. If you multiply a complex number by its conjugate, you get a real number. In fact, you always get a positive real number, which is kind of cool. If you add a number to its conjugate, you get a real number. So, if you picked a random complex number and you wanted to find another number so that when you added it to the original, you got a real answer, and when you multiplied it by the original, you get a real answer, the conjugate is the only possible choice. Okay, so if I, just as an example, if I wanted to go like 3 plus 2i times z is real, this does, yeah. And 3 plus 2i plus z is real. The only choice for z is 3 minus 2i. So the conjugate does that too. It's the only number that you can add to some other number, the only number you can add to the number you're thinking of, and multiply by the number you're thinking of to get a real answer both times. So this idea that when you multiply by the conjugate you get a real answer is what we use to rewrite our fraction when we were using Cartesian form. Right, and this, well, that works with polynomials too. So conjugation is really nice. You should know what conjugation looks like when you're using polar form and when you're using the picture as well. So in the picture, if this is z, then this is z bar. And if this is w, then this is w bar. Okay, it's a reflection in the x-axis. And the conjugate of cis theta is cis of minus theta. So when you do the conjugate of a cis, it's cis of the negative version of the angle. So that's how conjugation looks in the two other representations. There you go. So, I am going to put it back here because it's so nice to me. E to the z conjugate is e to the z conjugate. It works up there too in the power. It's just amazing conjugation. In case you ever do group theory, you may never, but it's a fun word to learn. Conjugation is an automorphism of the complex numbers. Meaning it's something that preserves both addition and multiplication. Yeah. It's the only automorphism of the complex numbers that leaves all the real numbers unchanged. It's kind of cool. Okay. Rightio. So where are we up to? We've done all these things. Actually, there's one other thing. Length. Length is important. We've talked about length when we did the polar form, but length is a thing that you can calculate on a complex number. Also known as modulus. So we've done it before. We figured out how far our complex number was from the centre. That's the modulus. So if you have a plus bi, the length of this, the modulus of this, is the square root of a squared plus b squared. Very important when you do this that you do not include the I when you calculate this thing. It's a literal length on the picture. And so therefore it has to be a positive number and it has to be a real number, and you're treating the b as a distance, not as b times I. So you use that when we use that when we calculated the polar form of a number, because we needed to use how far it was from the centre. But it's kind of important to know what it is as an operation. And it's important to know how it expands out over things. So it expands out over multiplication. That's important. It does not expand out over addition. Not true. Don't do it. Okay? It does not expand out over addition. As I said, the only thing that expands out over both addition and multiplication is conjugation. Okay? And it also expands out over powers, though. Well, it doesn't do that. You can bring the power out like that. The power is unchanged by the length. That works for cubes and whole number powers. It even works for integer powers. It works for 1 over as well. Oh, it does expand out over division. So in some sense, actually, modulus works the way a power does. Powers expand out over multiplication, but they don't expand out over addition. Okay. All right, how does it interact with conjugation? Because we've got this new rule. The length of the conjugate is the same as the length of the original. It's useful to know. What other operations can we do on things? I think that's pretty much everything that we can do. I keep calling it length. The official name is modulus, but it is a length, and it's easier for me to say that and to think about it that way. Yes. Now don't forget that this works with real numbers too. So if I had the length of 2i, that's the same as the length of 2 and times the length of I, and 2 is 2 long and I is 1 long. So it's 2. I know that I is 1 long because look, there it is. The distance from the centre is 1. Okay, and that's actually a useful thing to know. The length of cis theta for any theta at all is always 1. Because cis theta is a number on the unit circle, and so it's 1 away from the centre. Which means the length of 5 cis, I don't know, pi on 7 is the length of 5 times the length of cis pi on 7, because it expands out over multiplication, and the length of cis is 1. Yay. Now, technically you can go straight to here. but I just wanted to explain to you how these things work. Okay, 5 isn't just the description of the length of this complex number, it's an actual number, it's the number 5. So you can do it this way if you like. Right, there you go, complex numbers and everything you could possibly do to them. The only other thing you could do to complex numbers is make functions out of them, which you've done, but you sort of didn't notice that you did it. If I can square them and I can add them and I can multiply them by stuff, then that means I can make polynomials out of them. So, you did polynomials, right? And you had real polynomials and they had complex roots. / zeros, depending on whether I'm thinking of my polynomial as an expression or a function. So, I can make functions that go from the complex numbers to the complex numbers. And I can attempt to figure out when those functions are equal to 0 and solve equations using them. They're all things that I can do. And I have a whole separate seminar that I've already done in the past on polynomials as they relate to complex numbers, but it's worth noting that every time you allow yourself to have complex number answers, then everything is really a complex number. Yes. All right, there you go. Oh, let me just step back to this thing, this thing. The conjugate, right? Because the conjugate's the only number that will both multiply and add to produce real numbers, that's one of the reasons why if you have a real polynomial and you have one complex root, the conjugate has to be there as well, because when you expand out that polynomial, you're going to end up multiplying those things together and adding them together. And you need both of those answers to be real when you expand it out. And so that's why the conjugate has to be there, because it's the only option to be able to produce that real number in both ways. Well, I've got about 5 minutes before my official time finishes. And so what I'm going to do is ask you if you have any other questions about complex numbers of any kind before I wrap that up.
Is that a pi on 7?
Yep.
Okay.
The reason I chose pi on 7 is that I didn't need to know what the angle was in order to know that it comes out as the length of cis pi on 7 is 1. So since all I wanted to know was the length, I don't really care about figuring out what that angle is. Hello?
Does the conjugate also work for subtraction?
Yes, the conjugate also expands out over subtraction as well. In fact, I should go back there and add it in while we were at it. Damn it. Z minus W. Conjugate. Damn it. Get myself all confused. Moral of the tale is don't rush. And it's supposed to be a minus. Right. The conjugate of Z minus W is the conjugate of Z minus the conjugate of W. It works for negation too. Like, well, I don't know where to put this, but anyway. The conjugate of minus Z is minus the conjugate of Z. So, it all works out the same. I mean, subtraction is really just addition anyway, so well, I'd expect it to work for subtraction, but sometimes things don't work for both. So. Okay. Any other thoughts? I did have one other thing I wanted to show you, which I was very proud of. So I'll see if I can find it. I made this problem. Fill in each box with a different number from 1 to 9 so that this is as close as possible to I. So I'm going to ask you some questions. What do you notice about what's written there? Sorry? Well, I suppose that's the conjugate of something, certainly. Whatever root box plus box I is, that would be the conjugate of that. The thing I noticed when I made it was that I have a number in polar form and a number in rectangular form. That's going to make it a bit tricky to multiply. Not too bad. What would you do if you were faced with a number in polar form and a number in Cartesian form and you had to multiply them? What would your first instinct be? So just for the recording, convert the one in Cartesian form to polar form. It's a perfectly good thing to do. Multiplication is easier in polar form, so that seems like a reasonable thing to do. However, there's nothing stopping you, if you really wanted to, converting the one in polar form to Cartesian form, and then they're both in the same format. There's also nothing stopping you from just expanding these brackets and doing this times root thing and this times minus thing I, and having two different things. But of course, subtraction of things in polar form is not easy, so it's probably not the best thing to do, but you never know. There you go, kind of fun. What do you think would need to happen in order for this to come out to the answer I? Sorry? Get an angle of pi on 2. That'd be cool. All right. So we've got an angle here, and we could figure out what the angle of this is if we knew what the numbers were, but we get to choose what they are. So as long as the two angles added up to pi on 2, we'd be good, because when you multiply things, complex numbers, you add their angles. What do you reckon is going to need to go in these boxes over here in order for the angle for this to be pi on 2? Well, not pi on 2, just something that I know. I want you to imagine complex numbers that we've converted to polar form before that have roots in them. And see if we could try something. Anyway, you can do that in your own life as you practice for this. This will be really good practice for complex numbers. I think that a very good thing to do for yourself while you are studying is not always only to do exam-style questions, but sometimes give yourself backwards questions like this, where you have to work backwards to try and figure out how things fit together, because that makes you better at all of the things. And being able to do something backwards makes it much easier to do it forwards. All right, there you go. There's some morals of the tale for you. Don't forget, Maths Learning Centre is open all the way until the end of exams. I mean, for this exam, I'm told that you don't have to wait till the end of exams to do this one, but you may have other exams and you can come and talk to us about the maths in there. And be aware that we are also open during the second and third week of the university break. So if, God forbid, you need to do a replacement exam, you can still come and talk to us during the break. Hey there.
I missed last week's review lecture. Where can I find it?
It's on the Maths Learning Centre website,
Yeah.
which is... Okay, so if you go to the front page of the university,
Search Maths Learning Center.
yep, you can search for Maths Learning Centre, but you can also go there. And then under Resources, there it is, Maths 1M.
Yeah.
So, what did I do last week? I did trig, didn't I? There it is, 2017.
Oh, yes.
But there, I mean, all the past ones I've ever done are all there, so you know, no particular reason you need to look for last year's, this year's. Hey there. How's it going?
So,
With the sample exam that we've got given,
Yeah.
I've had a look over this question. I just really can't understand it.
All right. Let's.
And there was one in the making
Have a look.
TAs that I couldn't.
So z plus 2I times z bar is minus 5I. All right, well, I might as well just switch over to document camera and it'll be on the recording for everybody else. Okay, so we want to try and solve this equation. Okay. I don't like that z bar being there. That's making things not nice. Well, I have a couple of ideas. I could try and move things around. Oh, that's interesting. I don't know. I could try and move things around so it was easier to deal with them. But I don't know. It's not looking fun, is it? Well, all right. My first instinct is just to conjugate everything and see what I get.
Yep.
So if I conjugate this side, I can just do the conjugate of everything. So the conjugate of z is z bar, and the conjugate of 2i is minus 2i. And the conjugate of z bar is z again. And the conjugate of minus 5i is 5i. Yep? Okay. Right. Suppose if I added these together, then the 5i would go away.
Yeah. I guess.
So I'm going to have z and minus 2i lots of z. Yep. Mm-hmm. And I'm going to have z bar and plus 2i. What does that even mean? All right, so this is probably not the best approach.
Yeah.
It's worth a try.
Yeah.
I really have a feeling it's going to go there if I was concentrating very hard. Because like this is the conjugate of that, right?
Yeah.
Which means that I have a number and its conjugate adding to 0, which means that whatever that number is has to be an imaginary number. I can't have any real bits.
Okay.
Because when you add a number to its conjugate, you get twice the real part. So that's kind of cool. But that's just not going to help. Okay, well, let's try again.
Yep.
It was worth a try. We haven't done anything wrong, it just hasn't been helpful.
Yeah, yeah. That makes sense.
All right, well, the only thing I can think of now is to represent this in a different way. So what if I go like that? Because then I can go that a plus bi plus 2i times a minus bi is minus 5i. So what have we got? All right, sure, and why not? I should tell the reader that A and B are real because there's nothing stopping them being imaginary. Okay, so I times I is minus 1, and minus 1 times that minus would be a plus, so we get 2b there. Okay, sure. Well, these are both real, and these are all imaginary. Like that. So, If these two complex numbers are the same complex number, then they must have the same real bit and the same imaginary bit.
Okay.
Like this is like 0 minus 5i. Like it's got a 0 as its real part.
Yep.
And so I can, a plus 2b must be 0, and b plus 2a must be minus 5.
Okay.
So we're going to be subtracting and adding equations again, I reckon. I'm just going to line them up if that's okay.
Yep.
So if I did, it's even easier, right? So this minus that. No. If I do 2 of this one, 2 times number 1 gives me 2a plus 4b equals 0. Yep. And I'll call that number 3, and I'll do 3 minus 2
Okay.
to get rid of the a.
Yep.
So this minus that would give me 0. I'm going to get 3b equals minus 5, no, plus 5. Because I'm doing this one like that one.
Yep.
And so I get that b is 5/3.
Okay. Yep.
And if b is 5/3, sub into number 1, we'll get a plus 2 lots of 5/3 is 0, so a is minus 10/3. And so my z is in fact 5, no, that was the a was the real bit. Minus 10/3 plus 5/3 of
Oh my god.
I. Okay, so
That clears that up.
yeah, classic trick at this point, which I should probably write down, is that we're equating parts, right?
Yeah.
So that equating parts, we did it with the polar form when we were solving roots, but it didn't work quite as well because the lengths matched, but the angles didn't have to match.
Yep.
But when you're doing in Cartesian form, the real bit has to match and the imaginary bit has to match if they're equal, and so you can make equations. I have a suspicion that I could possibly have gotten there if I'd done this, but I didn't know how.
Okay. Yeah.
But if you've got, my usual instinct is if you've got a number and its conjugate together in the same equation, this is probably the most productive way of doing it. Yeah. Oh, I didn't talk about how the different how to make sets of complex numbers and colour them in on the complex plane. I knew I'd missed something.
Oh, yeah. That's something I need to go over as well.
I reckon it's on one of the other ones, so I won't delete the old one. I'll just have them both there and say, look, they've got different things in them. This is all recording at the moment. I should probably stop it. You get some really interesting things happening when you can't stop echo recordings. Did you want to ask something, mate?
Yeah, I just wanted to ask if there will be another one of these sessions or...
No, I've had enough.
Okay.
2 is enough, but all the past ones are on the website, so feel free to go and have a look.
Okay, good.
Awesome. Thank you very much.